of times I just don't think about it. Okay. Other questions from the homework. I know that 3-1 can be really challenging, so I want to make sure that we take some time to go through the questions if you have them. Ria, go ahead. Do you have a question?
Yeah, number 19.
Okay.
From the homework, please.
Let me look. And I'm just pulling up whichever iteration it's giving me, so. And the chain rule is really, really important. That's why I really want to make sure we get this right. Here it is. Okay. Number 19. Mine is y equals 7x times e to the 5x. The 7 and the 5 are going to iterate. So yours might look slightly different, but it should be basically the same function. Okay. So you're going to be using the product rule here and split this up into two factors, 7x and e to the 5x. If you want to call one of them f and one of them g. Good. So f prime would be 7. And g prime, remember it's like you're taking e to the x, but you have e to the 5x. So you're going to multiply by the derivative of the inside function, and the inside function is 5x. So you have 5 times e to the 5x. I'm hoping that you'll get really good with taking these exponential derivatives because you'll see them all the time. So just bringing that exponent out front and then just using it that way. So let's go ahead and use the product rule. We're taking f prime times g plus f times g prime. And, you know, this is one that you could factor out the e to the 5x if you wanted to, but like I said, that's not required. It's not something I really want you to put a ton of focus on. I mostly want you to be able to find derivatives. So if you want to write this as 7 e to the 5x plus 35x e to the 5x, that would be perfect. Other questions on 19 or other questions on other homework problems? Go ahead. If you have them, let me know. If you want to just even mark it in the chat, I'm looking at the chat. I'm only looking at it when no one's using it, but looking at it right now. Just let me know. Sorry that I'm eating. I'm really, really hungry and I didn't eat earlier. I'm going to try to be discreet. Maybe I should turn my camera off. My son won't even sit next to me while I'm eating cottage cheese. He thinks it smells disgusting. He's just like, you need to leave. Like, or he'll just leave. He'll be like, I have to go. He's 6 and he's just very particular. He's like, that's disgusting. I'm out. No other questions from the homework? You know, my whole point of getting in here was I wanted to look at how the homework was going. Because I had concerns because I did not receive hardly any questions over the past couple of days, which really surprised me. But it looks like people, for the most part, finished the homework and did just fine. So I hope that's the case.
It was pretty straightforward.
Oh, good. Well, that's good to know. Right. My husband is home. Hold on. I have a crying child. Let me just real quick turn this thing off. Someone will get her eventually. I don't know what is happening over here. Just be difficult to. Yeah, so I'm responding to Greg's comment in the chat. The chain rule can get really confusing whenever you have like nested chain rule. So it's like there's an inside function inside the inside function. And there was one I did on the notes where it was like a function inside a function inside a function. And then it's hard to keep track of what you're doing at that point. Most of what we're going to be doing with the chain rule, you're just going to see, like, you're going to see it one time. So, I mean, sometimes two times. I mean, like something like, see, I'm looking through my office hour notes. Something like number 24, this is a pretty common thing that you're going to see. So this is double use of the chain rule, because when you take the derivative of the inside function, the inside function also has an inside function. So you're thinking of your inside function as sine 7x, but then this function also has an inside function of 7x. It's not just sine x, it's sine 7x. So that's a pretty typical place where you're going to see that you need to use the chain rule twice. Or, yeah, I mean, that's an accurate statement. By the way, I had mentioned this before. I have been posting the office hour notes to D2L. It's in the content tab, and I think it says like office hour notes or something. It's very straightforward. It's not hard to find. But if you're on our D2L page, which I'm going to right now, just to tell you exactly what it's called. Under the content tab, it's called office hour notes, and it'll say office hour, and then it'll have the date on it. So I should do a better job labeling what's what, because if you don't know what section we're in, you might not know. You'd be like number 24, but okay, what was that in? So this was in your 3.1 homework. So I'm trying to remember to put that at the top, and I think I did that for each one. But keep an eye on that, and then it'll say, 24, and then I worked out 26, for instance. So I'm putting those on D2L, and I really wanted to point it out because I think you'll find it helpful, and it'll save not only you time, but it'll save me time, because I have been referring some people when they ask me questions on WebAssign. I'll be like, oh, you know what? I actually did this one in the office hour, if you want to refer to the notes, because it's much easier for you to look at the written work versus me trying to type it out and explain it. It's much easier for you to see that. So please do check out the office hour notes, especially if you are struggling, because who knows, maybe one of the questions you were having a hard time with, I covered. And it'll help you to prepare for your exams also. I, for some reason, also thought the homework was a little bit longer, but it looks like it wasn't too crazy. 33 points. Okay. It's not too bad. I am planning tonight to have like a sit down and finish grading everybody's tests night, because I really want to get them back to you by tomorrow. I mean, electronically, I would like to have that feedback back to you. So, so that's my plan. Yes, Gerardo.
Just curious. You said that which one do you have to drop if we do one of them bad?
The test, you mean?
Yes.
I drop whichever one's lowest, and you're going to have 5 chapter exams. I'm not dropping the final. That's its own separate category. So your lowest test score will be dropped, whichever one that may be.
Okay, just wondering, see if.
Does that answer your question?
Yeah, I was just trying to make sure if it was a quiz or the test that you're gonna drop.
I do drop your lowest quiz also, but I can't remember if I put that in the syllabus. For some reason, I sometimes forget to write that in the syllabus. I don't know why. Maybe because quizzes are a newer thing for me. I only have started doing them since I've been online.
Oh, okay. All right, that's pretty much all I have for now.
Okay. Oh, and don't forget you have a quiz tomorrow. So your quiz tomorrow will cover 3.1 and 3.2, and I'm doing 3.2 like right now. Now, the reason it was so important, and I had mentioned this a few days ago, it's so important to have 3.1 down, because 3.2 you can't do if you don't know how to do 3.1. Everything we're doing today is very much focused on our ability to use the chain rule. Oh my gosh, you guys. I'm so excited too, because I can't tell you how much I love this chapter. I don't know why. I just love taking these derivatives, and I love using the chain rule. So I was really looking forward to tonight. Sometimes I'm kind of like, oh, I'd rather do something else. It's summer. I'd rather hang out and do nothing. But tonight, chain rule is where it's at. Anyway, let's get into implicit differentiation. 3.2. All right, so this is often needed for equations that don't represent functions, or maybe they're not easily solved for y. Remember that in order to have a function, your graph has to pass the vertical line test, and that doesn't always happen, and that's okay. It just means you don't have a function. But what we're going to talk about today is that you can still have an equation that doesn't represent a function, and you can still find its derivative. And we're not even really going to focus on, is it a function or not? It doesn't matter. We're just going to be finding derivatives of equations that may or may not represent functions. And it could just be an equation that is a function, but maybe we just have a really hard time solving it for y. And if we can't solve it for y, it makes it really hard to find the derivative. I'm going to give you some guidelines here. Basically, it's just some instructions for how to go through this process of implicit differentiation. So the first thing we're going to do is differentiate both sides of the equation with respect to x. So normally what we have done so far is you've had y equals, blah, 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 some function in x. We might not have that in this section. You might have a whole bunch of terms on one side of the equation and a whole bunch of terms on the other side. But we're going to differentiate both sides of the equation with respect to x. Now, when we differentiate y with respect to x, we have to chain on the derivative dy dx. So when differentiating y with respect to x, chain on dy dx. And you'll see what I mean in a minute. If your use of the chain rule is good, then you will be very good with this implicit differentiation. But some of them will be challenging, not going to lie. The next thing you're going to do is collect all the terms with dy dx on one side and all of the other terms on the other side. Doesn't matter which side is which as long as they're split up. Next, you're going to factor dy dx from one side. Whichever side has the dy dx's, you're going to factor it out. And then the last step is solve for dy dx. Because really, in the end, every time we take a derivative, that's what we're looking for, the derivative of y with respect to x. And if you'd like some examples, if you're kind of like, what the heck, why would I need this? When would I need it? if you want to think about implicit versus explicit equations are the kind that we've seen so far. Basically, they look, like this. Y equals something with a bunch of x's in it. Something like that. There's a y on one side by itself, and there are some sort of functions of x on the other side. An implicit equation might be written something like y squared minus x equals -1. A lot of times an equation like this is just left implicit because if you wanted to solve for y, you'd have to take a plus or minus on both sides because you'd get y squared equals x minus 1. And then you'd have to say y equals plus or minus the square root of x minus 1. And then you end up in kind of a mess. So usually something like this is written implicitly. And by the way, this is not a function because you can't, when you solve for y, you get the plus or minus. And anytime you have the plus or minus, that means you're not going to pass the vertical line test. So this one's not a function. And then maybe something where you have y's on both sides of the equation. So 2x minus the square root of y plus 5y squared. Again, this is not a function, but it's a situation where you have y's on both sides. It would be very hard to solve for y if you tried. So, so something like that would be implicit. So this is what we're going to be dealing with today. So this is before, this is pre 3.2, and then the implicit is what we're going to be looking at today, stuff like that. Alberto, do you have a question? You unmuted, so I'm not sure.
Oh, no, my bad.
Oh, that's fine. I just wanted to make sure. Sometimes people are shy. Okay. All right, any questions about these steps? If you're just generally confused, don't worry. I'm going to show you how they work and you'll get used to it. Right. Let's get to work. I'm very excited. As I previously stated, I'm going to just move to another page. I'm going to need a little bit more space than this page allows. Just a little bit, but enough that I'm going to switch pages. Example 1. Differentiate implicitly. And just to sort of give you a roadmap as to where we're going in this chapter. Oh, by the way, I redid our schedule a little bit today. Nothing too crazy, but we're cutting out 3.5. It's a really short section anyway. A lot of years I skip it. Last spring, I actually had time to cover it, which is pretty rare. But I'm going to take it out. I have to post it. I redid the schedule, and then I saved it, and I totally was like, oh, I'll post it later. It's like if I don't do it right then and there, then it takes too long. But we're going to focus on 3.1, 3.2, 3.3, 3.4 for this test. And you might be thinking, wow, that's only 4 sections. That's really not a lot. You'd be surprised how much of a test you can fill up with only 4 sections worth of material. So you learn the chain rule in 3.1. So that's your basis for all of these things. We're going to learn how to take implicit derivatives today. And that's going to be a big focus. Tomorrow, we'll talk about finding derivatives using inverse trig functions or involving inverse trig functions. And then some of your weekend work will be over logarithms. So I'm hoping to start the logs tomorrow, and then you can finish them over the weekend or whenever it is that you get to them. The only thing is, I emailed you about this. We don't have class Monday, July 5th. I should have gone to my better source when I was originally asked about this. But when I consulted the page that I went to with our course information on it, it wasn't on there. And I've never, ever, ever, I teach summer classes at ECC every summer for like the past 10 years. Anytime 4th of July is on a weekend, they don't observe it during the week. We just have like shorter classes or something, like slightly, they're like 5 minutes shorter. It's weird. So I've never seen them do that. So when I didn't see it pop up that way on my schedule, I was just like, okay, well, it's not there. And then when I emailed our division secretary about it, she was like, no, it's an ECC holiday. So very sorry for the bad information. But we don't have class July 5th. You, however, have a test scheduled. Sorry, I should have mentioned this earlier before I got into this. Test 3 is actually scheduled for July 7th, which is a Wednesday. Now, you'll have plenty of time. It's just that you won't have a lot of me time in between then. So we're going to do 3-3 and start 3-4 tomorrow, and then you'll finish 3-4 between tomorrow and Wednesday. And even though that's like 6 days for one section, which is almost unheard of in the summertime, still you won't really get much of a chance to ask questions about it except via email. So I'm going to see if I can, I'm going to chat with my husband and see if I can maybe add in an office hour in between Thursday and Wednesday, because I don't want you to feel like you're taking a test and you didn't get a chance to really ask questions. And if you don't have a lot of questions, that's fine. But it will only be the 4 sections. So it'll be 3-1 through 3-4. But they are all kind of loaded. Each one of them will take like a whole class period. So it's not like they're little sections, and then we're going to skip 3-5. But your test is still scheduled for July 7th. And because we omitted 3-5, we should, I mean, we really were right on schedule anyway. So we should be good for that. I had a little bit of extra time built in for that too. I don't even know why. So see how it goes over the weekend. Email me if you have questions. Make sure I know, because if I don't know, then I'll just think everyone's fine and that you don't need me. But if you feel like you need some time, I'm going to see if I can build in an office hour, maybe on like Monday or Tuesday. I know, well, technically Tuesday, because Monday's an ECC holiday. So maybe I'll try to do that. And then I'll give you a little bit of time to let that simmer a little bit more. Okay, so that's my plan. That off to the side. Questions there before I proceed with implicit differentiation, which I'm totally excited about. Okay. Note that this would be very hard to solve for y. And also it's very likely not a function because you have 2y to the 4th power. So we're going to go ahead and take this derivative implicitly, and you're going to scan this real quick and make sure that you don't have any need for the product rule or the chain rule. It's a good idea in advance to kind of know what you're getting into. And of course, for example, 1a, I just gave you a very straightforward problem where you only have terms that require the power rule, not the product rule, the power rule. So we're going to use that here. The difference is that when we take derivatives that involve y, we have to chain on a dy dx. Now, it's not a big deal. We're still going to take a derivative and just, as though it was an x, we're just going to take the derivative of y. We just have to tag that on. And you'll get used to that, but just you have to remember it. So what that's going to look like is using the power rule, 2 times 4 gives you 8. Keep the y, decrease your exponent by 1. And because we took a derivative of y, we have to tag on this dy dx. Okay, now, I also want to say, because I have students every semester who've taken Calc 1 before, and a lot of times it's the students who had Calc 1 in high school who do this. They will write it, I don't want you to do this, they'll write it like this. Instead of writing dy dx, they'll write y prime. And some books even teach you to do this. So if you've gotten into this habit and you're like, well, this is the way I want to do it, I would strongly urge you to not do that, because you're going to lose track of this y prime. And it's somehow going to end up getting multiplied in. Sometimes students mistake it for y to the 1st. Sometimes they don't notice the prime on it and they treat it like a y. It's very important that this dy dx sticks out to you and that you know what to do with it. I strongly urge you to not use y prime. And I know why students do it. It's because it's a lot faster to write y prime than it is to write dy dx. Please don't do it. Please write dy dx. I can't force you. But I'm telling you, I've seen a lot of students make errors with the y prime just because they lose the prime, they do something with the y, it somehow gets combined in and it's not supposed to. So be careful there. All right, so that's the first term. For the second term, you already have x as your variable. So you're just going to take the derivative the way you normally would. 3 times 2 is 6. Decrease the exponent by 1 and you get 6x. Now you don't have to tag on a dy dx here. You should not tag on a dy dx here because you took the derivative of x with respect to x. So dx is 1. You don't have to write it. The derivative of y is 1 dy dx. The derivative of y with respect to x is dy dx. And the derivative of x is 1. Another thing I'm going to caution you to look at is when you get to the right-hand side, a lot of times there's a constant on the right-hand side, and students forget to take the derivative on the right-hand side. They say, okay, this equals 5, and then they work on it. The derivative of 5 is 0. So try to remember to take the derivative of your constants. Okay, so we have just taken the derivative implicitly. We need to now follow our guidelines to get dy dx, because what we're really looking for in the end is the derivative of y with respect to x. I mean, that's what we've always done. You've had a y equals blah, 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 and at the end you get a derivative of y with respect to x. So we differentiated both sides, tagged on the dy dx's. Now we're going to collect all the terms with dy dx on one side and all the other terms on the other side. Now it's up to you what you want to do. I tend to leave my dy dx's on the left, but really it's more of just whatever is most convenient for the particular exercise that you're working on at the moment. So these two terms have a dy dx in them. I'm going to leave them right where they are. And then the non-dy dx terms I'm going to move to the other side. So that will become positive 1 and negative 6x. My next step is to factor the dy dx from whatever side it's on. So in my case, it's on the left-hand side. Now, as you work through a bunch of these, you might find that you start to combine steps 3 and 4, and that's fine. Now, remember that when you factor dy dx out of dy dx, you still get 1. You don't get 0. So remember that you have to have 2 terms if you started with 2 terms. So don't forget the plus 1. And then the last step is to solve for dy dx. And the way you're going to do that, and I'm going to rewrite mine just so it's very clear where it came from. I'm going to divide both sides by 8y cubed plus 1. And then I can cancel them out of the left-hand side. Now, again, you don't have to rewrite this. I'm doing it for the sake of my notes looking nicer. But here's your answer. Dy dx equals 1 minus 6x divided by 8y cubed plus 1. I have a couple things I want to say about this. First of all, does anyone have a question about how I obtained dy dx? One thing I wanted to say about this is, oh, go ahead, Renee.
So you just leave it as dy dx, you don't change it back to y or anything?
If you were going to change it to anything, you would change it to y prime, but y prime and dy dx are the same thing. If you remember when I gave you the notation, we kind of said you could write it this way, you can write it that way. No, I mean, but you just leave it as dy dx. That is your derivative. It's just written now in terms of 2 variables instead of 1.
Okay, thank you.
You're welcome. Any other questions? what I was going to mention was sometimes it's completely arbitrary which side we decide to put the dy dx's on. So in this step, I decided that I was going to leave the dy dx's on the left, and I was going to move the non-dy dx's to the right. Well, like I said, that's arbitrary. You might have left 6x and minus 1 on the left-hand side, and then on the right-hand side, you would have had 8y cubed minus 1 quantity times dy dx. If you had done that, your answer would be almost exactly the same. It would just have exactly opposite signs throughout the whole answer. So I want you to know that just because your answer maybe doesn't match mine or doesn't match, I don't know if WebAssign even shows you a key. I don't even know. I should really figure that out. But now that they're dropping our book, this is my last semester using WebAssign. So I guess I'm not too worried about it. But if you're looking even through the back of the book, and maybe their answer was listed as 6x minus 1 divided by -1 minus 8y cubed, well, it's as long as every single one of your signs is opposite, that's all that happened, is that the dy dx's were moved to the other side. And it might be the case. So it has to be every single sign, though. So when I'm grading and I'm kind of looking at my final answer, if your final answer is exactly the opposite signs, then I'm not too worried about it. Okay, so let's do another one, of course. So this one is 3xy plus twice the quantity x plus y cubed equals y. So now these are getting a little more complicated, because you can see now that we're going to need the chain rule here. Because we're not just taking x and cubing it, we're taking x plus y and cubing it. So that's going to require the chain rule. We also have a situation here where we're going to need the product rule, because we have x times y. So we have a couple of different things going on here that we're going to have to work with. Let's go ahead and just work this one left to right. When finding the derivative of xy or some constant multiple of that, this is really common. You're going to see this a lot, so hopefully you'll get used to doing this. I usually will just group together whatever first two factors are together, and then just put that third factor as the second part of your product rule, assuming your first factor is a constant multiple anyway. So if you want, you can think about 3x as being f and then y as being g. And I'll break this down for you since it's the first time you're seeing it. F prime would be 3, and g prime would be dy dx. So 1 dy dx, since you're taking the derivative of y with respect to x. But notice that for f prime, we didn't need to chain on the dy dx because we already were dealing with the variable x in that factor. We were taking the derivative of 3x. It didn't have a y in it. So let's go ahead and use the product rule for the first term and then focus on using the chain rule for the second. Okay, so f prime g. Now, when you write g, you don't need to tag on a dy dx because you haven't taken a derivative. So f prime g plus f, and then times g prime. So now, in this case, we have the 3 in front. If you're just taking the derivative of xy, you're going to get used to doing that. It's always going to be y plus x dy dx. In this case, we multiplied by 3 because we had that constant multiple here. All right, so this is the derivative of 3xy. Are there any questions so far? All right, now we'll use the chain rule. So go ahead and start to use the power rule as though you just had 2x cubed, and then we'll chain on the derivative of the inside function. So 2 times 3 is 6. Rewrite the inside function. Don't mess with it. Decrease the power by 1. And now you're going to chain on the derivative of the inside function. The derivative of x plus y is 1 plus dy dx. So this right here is the derivative with respect to x of the inside function x plus y. Okay, any questions on the chain rule usage here? On the right-hand side, you just have a y. The derivative of y with respect to x is dy dx. Now, I find that students have a hard time with this type of problem where they've had to use the chain rule and then they have this factor that has something else plus dy dx in it. You have to distribute into this expression because you need to have separate terms such that each term either has a dy dx on it or doesn't. Right now, this term has a non-dy dx and a dy dx being multiplied by it. So you're going to have to distribute so that you have each term actually in its own separate term. Now, the first 2 terms are fine. They're already separate. No big deal there. You can rewrite that. But now when you distribute, you're taking this entire quantity, 6 times x plus y squared, and you're going to distribute it into the parentheses. It's going to first get multiplied by the 1, and then it's going to get multiplied by dy dx. So 6 times x plus y squared times 1 just looks like this, 6 times x plus y squared. And then when you distribute that to the dy dx, just looks like that. Multiply it by dy dx. I don't know, students, they don't think to distribute for some reason, and then they get stuck and they're not sure how to solve for dy dx. If you want to solve for dy dx, it has to be in its own term. To solve for dy dx, it must be in its own terms. So it can't be combined with another term getting multiplied. So that's kind of where this part came in. All right, questions on this step? I guess I'm just breaking this down very slowly because I've had so many questions on these particular steps. So I'm just trying to preempt that. But now that you have separate terms, some of them have dy dx's, some of them don't, you decide where you want them to go. What I tend to do is any side that has more dy dx's, I leave it on that side. So the left-hand side has 2 of them, I'm going to leave them there. So that means that this one from the right-hand side is going to come over. So I'm going to have 3x dy dx plus 6 times x plus y quantity squared dy dx. And then I'm going to subtract the dy dx off the right-hand side equals, and then all the non-dy dx terms I'm going to move to the right-hand side. So this 3y, it's going to the right-hand side. And remember, change the side, change the sign. Same with the 6 times x plus y squared. Change the side, change the sign. And then count and make sure you still have as many terms as you started with. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now, this is where, when you've done this a lot, you might just jump right to writing dy dx equals, and then showing that in 1 step versus 2. I'm going to show mine factored, and then I'm going to solve for dy dx, just because I don't want to skip too many steps, but I don't want you to feel like you have to show both, because you are going to get pretty quick with seeing these. Just don't forget when you factor dy dx out of dy dx, don't forget your 1. That's a very common error. And then divide both sides by the factor of dy dx on the left. So you're going to end up solving for dy dx and getting negative 3y minus 6 times x plus y squared divided by 3x plus 6 times x plus y squared minus 1. And that is your answer. Whatever you do, don't cancel the 6 times x plus y quantity squareds. You cannot cancel them because you cannot factor them out of the numerator and denominator. All right, are there questions here?
Yeah, so I had a question on
Go
the second step.
Okay.
How did you get these the second 6x plus y squared?
This one?
Yeah.
Okay, so this came from, I had this quantity, 6 times x plus y squared, and it was getting multiplied by this binomial, 1 plus dy dx. So we took this and distributed it into the parentheses. So first we multiplied it by 1, and then we added that to the product of 6 times x plus y squared and dy dx.
Okay, thank you.
You're welcome. That's always a question I get, so I'm glad you asked.
So you essentially just took the entire thing and distributed it that way.
Yep, exactly.
Okay.
Yeah, I think sometimes students are just confused about when they need to do that. And when you need to do that is when dy dx is inside some sort of grouping symbols with non-dy dx's getting multiplied by a quantity. You'll see that more often than you might imagine. But usually it involves some sort of chain rule usage that then you have to split that up into its own term. Because otherwise, how would you solve for dy dx if you didn't distribute? You wouldn't have it in its own terms. You'd be stuck. Nobody wants to be stuck. Nobody. And we're going to use that again. Actually, in my next example, we're going to do that again with the use of the chain rule, with a trig question. So if you feel like, I think I got it, but I'm not sure, you're going to see it again. And ask me again if you need further clarification. Other questions, though, on B? So you kind of see how this class really just kind of gets more complicated. I mean, last week we were just doing derivatives of like 4x squared, and now here we are. So it escalates quickly, especially in the summer. Okay. C, we'll do a trig function. Students always need more work using trig with the chain rule. Always, always, always. Oh my gosh, you guys. Not only is this needing the chain rule, because I don't just have sine x, I have sine of some function of x. The function that I have is a product. So this one is going to need the chain rule and the product rule. And again, students are always kind of stuck on, well, how do I know when I need this? How do I know when I need that? A lot of times it's just practicing a lot, getting a good feel for what's happening. I mean, I can tell you the technical reason why you need it. Technically, you don't just have sine x. Anytime you're taking a trig function and the inside function is something other than just x, you need the chain rule. And if you're multiplying two functions together, it's not just 2x. It's not like it's a constant multiple. It's these two variable functions that tells you that you need the product rule. So we're going to take the chain rule, and then when we take the derivative of the inside function, we're going to be using the product rule. And if you'd like, I'm going to write this out in 2 steps to try to make this super clear. And if it makes it less clear to you, sorry, try to skip the step. But I'm going to try to denote this so that it's very clear when it happens. Okay, so we're going to take the derivative as though we just had sine x, but then we're going to chain on the derivative of the inside function. All right. So the derivative of sine x is cosine x. So we're going to take cosine and, just rewrite the inside function like nothing happened. But then we need to multiply by the derivative of the inside function, which is going to be this guy. I'll do that in the next step. Okay, now on the right-hand side, the x squared, well, that's our standard derivative, 2x. The derivative of y is 1 dy dx. You can write the 1 if you'd like. Otherwise, don't write it. It's fine. Okay, but here's where our chain rule comes in. And when you're taking the derivative of xy, this is where your product rule comes in. Now, we did this product in the last example. If it's not as obvious, you saw it as 3xy. We can look at f and g. My notation is getting real crazy here because there's a lot of stuff I want to say. So we'll let f be x, g can be y. And then f prime is 1, g prime is dy dx.
I have a question.
Yes, go ahead.
Why is it not 1 for x?
Y is, wait, say that again?
Did you do like the derivative of x as y?
Oh, so I'm just looking at this product, and taking the derivative of x is always going to be 1. So as long as I have the x variable, I can take the derivative normally.
Oh, I thought you were doing like that, not like, okay, I see now.
You got it? Okay, that's fine.
Yeah.
Other questions here? Wonderful. Okay, so I'm going to rewrite my cosine xy, and then I'm going to multiply by the derivative of the inside function. So f prime g, which is 1 times y, plus f g prime. And like I said, you should get really used to taking the derivative of xy. You're going to see xy all the time. Its derivative is always going to be y plus x dy dx for this very reason. Rewrite the right-hand side. We haven't done anything there. Okay, now I promised you that you were going to have to do some distributing here, and here's where it is. By the way, I said it before. I'm going to say it again. You cannot multiply xy by what comes behind it. All right, remember that this quantity right here is being multiplied by your cosine function. It's not being multiplied by xy. So if you would like to put some brackets around that just to make sure you know what you're doing, that's fine. But what we're going to do here is we're going to distribute the cosine xy into the parentheses. And again, we have to do this because if we're going to solve for dy dx, we need for it to be in its own separate terms. And right now, it's getting multiplied by a non-dy dx and the cosine xy all together. I need for it to just be a dy dx or a non-dy dx. When I distribute, I'm going to put these values in front of the trig function just because I don't want to accidentally multiply them into the angle. You can tell I've seen this mistake a lot, so I just want to make sure it doesn't happen. So we have y times the cosine of xy plus x dy dx times the cosine of xy plus 2x, I'm sorry, equals, not plus, equals 2x plus dy dx. Okay, so we distributed here. And it does not matter what order you multiply these in. It could be cosine xy times dy dx times x. As long as they're all getting multiplied together, I just think they look better for me in this order. Okay, questions here? Now, anything with the dy dx on it, I want on one side. Any other terms are going to go to the other side. I'm probably just going to leave this one here. I don't know why. A lot of times I just leave the left alone. X dy dx cosine xy, and then I'm going to take the dy dx from the right and subtract it over to the left. And then everything else, this 2x is going to stay on the right. And then the y cos xy, I'm going to move to the other side, change the sign. You started out with 4 terms, you still have 4 terms. Double check their signs. Okay, questions here? Okay, now factor out the dy dx, and then we'll solve. So when I take that out, don't forget you still have an x times cosine xy, and then don't forget your 1 equals 2x minus y cosine xy. And then to solve for dy dx, you're going to divide both sides by that factor of dy dx that you see on the left. So leave the right-hand side alone as your numerator. And then divide by x cosine xy minus 1. Questions on that one? All right, for D, I want to do one with an exponential function in it. I'm going to show you guys all kinds of examples. Always want to try to do an exponential and a trig. This is going to be e to the xy. Again, you're seeing that we're going to need the chain rule and the product rule. Plus x squared minus y squared equals 10. Since we know we're going to need the chain rule and the product rule, if you want to go ahead and use the product rule, again, we've done this product. This will be our 3rd time now. So if you want to do it off to the side so that I don't have to pop it in to the notes here. The derivative of xy, remember that you're going to let f be x and y will be g. f prime will be 1, g prime will be dy dx. And your derivative then will be f prime g plus f g prime. Okay, so we're going to use that here in a minute. When we take this derivative, we're going to use the chain rule. And if you want, I mean, this is something that we're referring back to. This is the third time now in 4 examples. It comes up a lot. If you want to put a box around it, highlight it so that you can easily find it again, you might find that to be beneficial to you. All right, let's go ahead and take this derivative. The derivative of e to the x is just e to the x. However, we have e to the xy. So you're going to take the derivative like you normally would, but then you're going to chain on the derivative of the inside function. So we'll keep it as e to the xy, chain on the derivative of xy. We just found that over here. It's y plus x dy dx. And look at that. We're having another example where we're going to have to distribute in the next step. Plus 2x minus 2y. Don't forget when you take the derivative of y to chain on that dy dx. And the right-hand side, don't forget to take the derivative of 10 to get 0. Questions on the derivative? We still have to simplify it, but technically this is the derivative. Okay, so we are going to distribute, and remember we have to do this because we need to have dy dx in its own term. Otherwise we can't solve for it. So we'll have y e to the xy plus x e to the xy dy dx plus 2x minus 2y dy dx equals 0. Questions here? Okay. Now, once you're here, this is the easy part. You've already done the hard part. Really, the hard part was just this first line, taking the derivative. Now you're just solving for dy dx. I'm probably just going to leave them on the left. If you want to move yours to the right, fine. Does not matter to me. Anything that does not have a dy dx on it, I'm going to subtract off the other side. So let's see, minus y e to the xy minus 2x. So I moved this guy and that one. And I only had 1, 2, 3, 4, technically 5 terms if you include the 0. Everything matches up. Factor the dy dx and solve. And here's where if you want to do factor and solve in one step, I'm totally okay with that. Right-hand side hasn't changed. All we did was we factored dy dx out of the left-hand side. And now to finish this one, divide both sides of your equation by x e to the xy minus 2y to solve for dy dx. So you'll have negative y e to the xy minus 2x divided by x e to the xy minus 2y. Questions there?
So right up top, where did the 2y get the dy dx from?
This one?
Yeah.
Any term that you take for which you take a derivative, if it's got a y in it, it gets dy dx.
Okay. Okay.
Anyone else?
I have a question.
Go ahead.
When you were distributing e to the xy, why didn't you put another xy for dy dx?
So that one is right here. So we had x dy dx, and then we multiplied it by e to the xy.
Oh,
You see what I'm saying?
I think so. Okay.
Okay, so when I distributed, I took the e to the xy and multiplied it by y, which is right here, brought down the plus, and then I multiplied it by x, dy dx. I did sort of switch the order of the multiplication, but all the factors are still the same.
Okay.
Is that clear?
Yeah.
Okay,
Thank you.
you're welcome. I'm always glad when you guys ask questions. Are there other questions here? It also makes me feel less like I'm teaching into the abyss. Okay, we're going to shift gears here for a minute. We're going to come back to these implicit derivatives. But remember how I was telling you that your book is super weird because it breaks down the power rule so many times? Well, you're finally seeing the last piece of that now. So I'm just going to give you that. Take a little breather. Power rule for rational exponents. Remember that rational exponents are exponents that can be written as fractions. So usually when we see rational, we think fractional. So I gave you a power rule for natural numbers. Then I gave you a power rule for any integer, saying that your exponent could be negative or positive. And here it is for fractional exponents. And I'm going to give you the rule, and you're going to be like, okay, didn't we already know this? Kind of, but you're officially, formally getting the rule now. If y equals x to the power p over q, where p over q is a rational number, which means it can be written as a fraction. Then y prime is equal to the derivative with respect to x of x to the p over q. And this derivative is bring the exponent down, rewrite the x, subtract 1 from the exponent. So basically nothing new, but you're officially being given this rule now that you can use this for fractional exponents. And of course, I'm going to show you some examples of this. It will apply to functions of x, so it doesn't necessarily have to be just x to the p over q. So here's the second piece of this. If u is a differentiable function of x, and r is a rational number, then the derivative with respect to x of your function u of x to some fractional power r is equal to r times u to the x. Take 1 off the power, chain on the derivative of the inside function. So this is basically just saying you can use the chain rule with this power rule for rational exponents. This is provided u to the r and u to the r minus 1 are defined. I mean, we can't take the derivative all the time. As you know, we talked about when a function might not be differentiable, finding places where the derivative does not exist, but most of the time you don't have to worry about that. In the next chapter, we'll focus on really finding those places, but for right now, I just want you to find derivatives. So I'm going to give you some examples of using this power rule for rational exponents. It's going to be very similar to what we did in some of the sections of chapter 2. Just this time you'll see this a little bit with, you'll see all of them with fractional exponents, and some of them might need the chain rule. So example 2, find the derivative. The first one will be y equals x to the 4/5 power plus 7 times x to the 2/3 power.
I'm sorry, can I see the last part again from the previous page?
Oh, sure. I took it away too soon.
Okay, I got it.
Okay,
Thank you.
no problem. Okay. All right, let's go ahead and take our derivative using this power rule for rational exponents. All right, so first we're going to bring the power down. You're going to rewrite your variable, and you're going to subtract 1 from the exponent. Now, you're going to get good at doing this because you're going to do it so often. If you want to do it in your calculator, fine. But just write 1 as 5/5, and then you'll make your life a lot easier. Oh. For the second term, leave your constant multiple, multiply by the exponent, keep your variable, and subtract 1 from the exponent. And we'll simplify. So same as what we did last week, it's just that now we're saying we can do this for rational exponents and not just integer exponents. So we'll have 4/5 times, okay, now 1 is 5/5. So 4/5 minus 5/5 is -1/5. And then plus 14/3 x to the 1 is 3/3, so 2/3 minus 3/3 is -1/3. I'm totally fine with you leaving your answer like this. If you want to write it with positive exponents, you can. Sometimes I just like to show it like that because I think it's good for us to get the practice. But it would look like this: 4/5x to the 1/5. So moving that exponent into the denominator, you can change the sign. And then 14 divided by 3x to the 1/3 power. So that would be an equivalent answer, but the one in the box is just fine. Questions on A? For B, we're going to work on our radicals a little bit. This will be the square root of x plus 1 over the 4th root of x. So this is not 4 times the square root of x. The 4 is in the index. And then if you don't remember, most of us do remember, but just in case, I never know. The square root of x is x to the 1/2 power. If you don't see an index, it's assumed to be 2. And you also had a property that the nth root of x to the mth power could also be written as the nth root of x to the m. And you could write that as x to the m over n. So we're going to use this when we're converting our radicals to rational exponents. Because remember, in order to use this rational exponent power rule, we need to be able to actually write our expressions using rational exponents. The index of your radical is always the denominator of the fraction. Whatever the power is always going to be the numerator of your fraction. And these two are interchangeable. It kind of depends on which one you need most at that moment. So I'm going to rewrite this expression using rational exponents. We have y equals x to the 1/2 power. And then we have plus 1 over x to the 1/4 power. And we're going to write this again. We haven't taken a derivative yet. Right now, I'm just rewriting the original function so I can actually get it written with rational exponents. So your index is always going to be the denominator of your fraction. If you don't see an exponent, assume it's 1. So I want to make my exponent, or I want my expression to be in the numerator. Technically, right now, with my variable in the denominator, I would have to use the quotient rule. I don't want to use the quotient rule if I don't have to. But if I pull this x up into the numerator, I can change the sign on the exponent, and now I can use that power rule, and I don't have to worry about using the quotient rule. I've just saved myself a lot of time and effort there. All right, so now our expression is ready. Any questions on how I've rewritten y? So let's take the derivative, bring your exponent out front, and subtract 1 from the exponent. I'm not going to keep writing -1. If you want to check me in your calculator, feel free. 1/2 minus 1 is -1/2. And again, I'm going to bring the exponent out front. Instead of writing plus a negative, I'm going to go straight to minus. We should feel pretty comfortable with that by now. X to the -1/4 minus 1 is -1/4 minus 4/4, which is -5/4. Again, put that in your calculator if you need to. I don't want you sitting here banging your head open for these fractions. That's not a battle that I want to fight with you guys. It's done. Stick a fork in it. If you want to write it with positive exponents, if we can even convert this back to radicals if you want to. It would look like this. Technically, I feel like I should remind you guys of a property right now. I'm going to, because I think it'll help you if you're going through the book and you're trying to compare your answers and you're like, how did they get that? Recall, I'm going to remind you of some rules here from algebra. X to the 5/4 is really just x to the 1st times x to the 1/4. And if you want me to split it up twice, remember if you're multiplying and you have the same base, you add the exponents. So this would be x to the 4/4 plus 1/4, which is x to the 5/4, right? This is just x times x to the 1/4, which is really just x times the 4th root of x. So if you were trying to rewrite this, if you wanted to, you don't have to. I don't know. I just feel like it's always good to practice our algebra skills. You could even rewrite this here as minus 1 over 4x times the fourth root of x. And these are all equivalent expressions. They're all saying the same thing. It's just, what do you want to say? I mean, obviously, don't go crazy rewriting your forms, because I certainly don't want your derivative to be wrong because you've rewritten it so many times and missed a rule. Like I said, I think it's good to go over these algebra rules because you never know when they're going to pop up. But this answer is perfectly acceptable. Questions here? My next one will use the chain rule and the product rule. Yes. My two favorite rules, especially when used in conjunction with each other. C, y equals 3x squared times the square root of x to the fifth plus 2. Okay, so we're going to be using that product rule for rational forms right now, for rational exponents. So you're going to want to rewrite this using rational exponents. We're taking x to the fifth plus 2 to the 1/2 power. Anytime we're square rooting a quantity, we're taking it to the 1/2 power, the whole thing. So don't forget your parentheses. Also, now might be a good time to remind you that this is not equal to x to the fifth to the 1/2 plus 2 to the 1/2. This is a big no. You cannot distribute the exponent into the terms of the expression. Don't do that. That would be like saying you could take the square root of x to the fifth plus the square root of 2 and it'd be the same quantity. It's not. I always feel like I should mention that. All right, so here we're going to need the product rule and the chain rule. I'm clearly multiplying the product of two functions of x here. This particular one is going to need the chain rule because I'm taking some quantity to the 1/2 power, some function of x to the 1/2. It's not just x to the 1/2. It's x to the fifth plus 2 to the 1/2. So if you want to label these two parts f and g, we'll find their components, and then we'll put this derivative together using the product rule and the chain rule. Okay, so I'm not worried about f prime. F prime is 6x. G prime is where our chain rule comes in. So we're going to take the derivative starting out as though this was just x to the 1/2. So we're going to bring the power down, leave the inside function alone, subtract 1 from the exponent. And then here's where we're going to chain on the derivative of the inside function. So the derivative of x to the fifth plus 2 is 5x to the fourth. So remember that this quantity is the derivative of x to the fifth plus 2. Okay, now we haven't actually taken our real derivative yet. We've only just found the components for the product rule. Now we have to apply the product rule. Before I continue, does anybody have a question on what we've done so far? F prime G plus F times G prime. Now, I do want you to simplify this at least a little bit. You might find that the book answer or the WebAssign answer is very different from the answer that you got. And a lot of times what they end up doing is they factor out x to the 5th plus 2 to the 1/2 power, and then their answer looks very different once they factor it. I don't care if you factor it or not. I would much rather you just simplify what you can. What I mean by that is the first term, there's really nothing you can simplify because you can't multiply this into the radical. I mean, really, it is a radical. It's the 1/2 power. So the first term is simplified. What I do want you to do, though, is combine any monomials that need to be multiplied and any constant multiples. So the 3 times the 1/2 times the 5, that should get multiplied. So 3 times 5 is 15. 1/2 times 15 is 15 halves. And then you have x squared and x to the 4th. If you're multiplying and you have the same base, you add the exponents. So you'll get x to the 6th. And then leave this expression alone if you want. Don't feel like you need to get real crazy. This is perfectly acceptable for me. It's wonderful. I'll be very happy. This is technically your derivative and it's simplified. It's done. Go ahead, Morgan.
So if you put, instead of the like parentheses, x to the 5th plus 2, and then like 1/2, if you just do like the square root of x to the 5th plus 2, will you get the wrong answer?
You would have to put it, I'll write the square rooted answer and you tell me if you still have a question about it. So if you want to convert it to a radical, you can. Just make sure that everything's where it's supposed to be. So a positive exponent means your radical stays right where it is. And then for the next piece, since you have a negative exponent, that radical would pop into the denominator. So you could write this, and I'm going to leave the 2 in the denominator because it was already there. The 15x to the 6th would go in the numerator. And then in the denominator, you'd write the square root of x to the 5th plus 2. And that would be the equivalent way of writing it. Does that answer your question?
Yeah, that makes sense.
Okay. Yeah, so do that if you want. If you don't, fine. But like I said, I do think it's good to kind of work our way back and forth. I have one more of these with the trig function in it because why not? Should always do more trig. I got my kids to the point now where they ask for getting jiggy with it in the car, which I really don't mind. I mean, they're little, but it's really not that inappropriate. And it goes so fast. They don't know what he's saying. It's not that bad. It could be a lot worse. They're really obsessed with the weekend right now, and I'm trying to wean them off of that because it's very inappropriate for little ones. I blame my husband. Oh, I bring up getting jiggy with it because we're getting tricky with it right now. Y equals, all right, your parentheses are really, really important here. In parentheses, x sine x, and that entire quantity is being taken to the 5/2 power. All right, look at your function and see what's happening here. You have a product that's being taken to a power. Now, when you take the derivative using the product rule, it's going to look very much like x to the 5/2, but you're going to have to chain on the derivative of the inside function. So we're going to say it also needs the chain rule. So this problem in and of itself, it doesn't look too crazy, but you're going to find it's really not that crazy. You just have to make sure that you're actually applying the rules that are required. So we got a couple different things going on here. Now, sometimes if you don't notice right away what's happening, just start to take the derivative and kind of see where you end up. Because sometimes maybe it's not obvious right away that you need the product rule and the chain rule, but you're going to get going on it and then be like, wait a second, I'm missing something, and then it will hit you as you work through it. All right, so we're going to treat this like it's x to the 5/2, but we're going to chain on the derivative of the inside function. So we're going to bring down the exponent, rewrite the x sine x, decrease the exponent by 1. So 5/2 minus 2/2 is 3/2. And then we're going to chain on the derivative. I'm going to write this in 2 steps of the inside function. Does anyone have a question here? Okay. Wonderful. So now we're going to take the derivative of x times the sine of x. And this is where the product rule comes in. So if you want to think of this guy as f and sine of x as g, f prime is 1, g prime is cosine x. Now the first factor we're going to leave alone. We don't need to do anything to it. So it's going to stay 5/2 times x sine x to the 3/2. When we chain on the derivative of the inside function, let's remember to use parentheses because we're going to get more than one term here. If you want to use brackets even, that's fine. Up to you. I'm just going to use parentheses in this case. All right, so product rule, f prime g. So 1 times the sine of x plus f g prime. And really, there's not a whole lot more you can do here. I mean, you could distribute, but I don't see the need to. Why would you? It's factored. I would say it's done. Stick a fork in it. Okay, so that was your little mini breather away from the implicit derivatives, which we're about to get back to. Okay, now. Trying to see. Okay. All right. Questions on D before I get back into these implicit derivatives? Now, really, I just want you to see more implicit derivatives, but also we're going to add a piece on here for finding the equation of the tangent line. So example 3, find the equation of the tangent line. At the given point. And we're going to work on some more of these implicit derivatives. We have x squared plus xy minus y cubed equals 7. And again, you're seeing this xy. We found this derivative now 3 times at least. We're going to recall from our previous examples that the derivative of xy is f prime g plus f g prime. So we're going to use that liberally. I'm going to use it again. So I'm just popping it off to the side here. But as far as the other terms are concerned, I only need the product rule for xy. And then the other terms, we're just going to take the derivatives of normally. Now, when I take the derivative of y cubed, I'm going to have to chain on dy dx just because the variable is y. But other than that, nothing too crazy going on here. Oh, and I didn't give you the point. Whoops. At the point 3, 2. Otherwise, there's no point in doing this example. We've already done some like this. So let's go ahead and take the derivative. We have 2x. We don't need a dy dx because the variable is x, plus the derivative of xy is y plus x dy dx. So that is using your product rule. The derivative of y cubed is minus 3y squared. Don't forget to tag on or chain on your dy dx because you're taking a derivative of y with respect to x. And then don't forget to take the derivative on the right-hand side. The derivative of 7 is 0. All right, questions about the derivative. We still have to simplify, but this is where any of the questions you have will occur right here. Everything else is just algebra. All right, all the dy dx's are going to stay, I'm going to say, on the left. You can move yours to the right if you want. I don't know, it's up to you. You know what? Let's change it up. I'm going to move mine to the right. I also sometimes like for more terms to be positive than negative. And since I have already 2 positive non-dy dx's, maybe we'll leave them on the left, move everything else over. Up to you. 3y squared dy dx will move to the right and become positive, and then minus x dy dx will move it to the right and make it negative. Now, if you already left your dy dx's on the left and you want to work through this, that's fine. You can check your work against mine, and you'll notice that in your answer for dy dx, your derivative will have the exact opposite signs on each term, which is fine. So I'm going to factor out the dy dx. That leaves me with 3y squared minus x. And then we'll divide both sides by the factor of dy dx. And we'll get 2x plus y divided by 3y squared minus x. Now we still have to evaluate this at the point 3,2 and find the equation of the tangent line. So here's your derivative. If you left your dy dx's on the left, your derivative would look like this. All of your signs will just be flipped. That's it. No big deal. This is mine. So here's my derivative. I'm going to find now the slope at the point 3,2. Now, normally when we find the slope at any given point, we usually have a derivative that is written all with respect to x. So we don't need to worry about the y coordinate. In this case, we need to really use both of these quantities. So I'm going to take my derivative, and I'm going to evaluate it at the point 3,2. And usually when we say we're going to evaluate something, we kind of leave this vertical line, and then it just kind of says like, okay, we're evaluating it at this point. So everywhere I see x, I'm going to plug in 3. And everywhere I see y, I'm going to substitute 2. Don't mix those up. It's very easy to mix up. So 2 times 3 plus 2 divided by 3 times 2 squared minus 3. Um, 6 plus 2 is 8. 2 squared is 4 times 3 is 12 minus 3 is 9. So this is your slope, 8/9. Questions on the slope? So now we're just going to take our point, which is 3, 2, and we're going to write an equation for the tangent line. So y minus y sub 1, which is 2, equals m times x minus x sub 1, which is 3. And then you'll simplify. We should have done this so much by now. It is just second nature to us. By the way, 24/9 we can reduce as 8/3. So all right, y equals 8/9 x minus 8/3 plus 2. And 2 is just 6/3. So minus 8/3 plus 6/3 is minus 2/3. So I don't want to forget my x. And that's the equation for the tangent line for this graph. Now, I'm trying to think if there is a way. Yes, you know what? Let me do it real quick and then I'll share my screen. I don't know if you guys ever use Desmos, D-E-S-M-O-S. I'm going to share my screen in a second. Let me see if this will graph, and if it does, I'll show it to you. It should graph. I use Desmos a ton. So loud. All right, yes. All right, I'm going to share my screen. Let me see. Stop presenting. Okay. So if you Google Desmos, D-E-S-M-O-S, when you Google it, it comes up with a few different options. I would select graphing calculator, and that's how I got here. I don't know what actually happens if you just go to desmos.com. I'm sure you just select graphing calculator. Math tools. Yeah, so if you go to desmos.com, share this tab instead. And then you go to math tools. It's under graphing calculator. That's how you would get this. So I'm going to go back to my tab. So our original, I don't want to say function, but if you go back to, we're on example 3a, the equation that I gave you was x squared plus xy minus y cubed equals 7. This calculator will graph non-functions for you so that you can actually see. I mean, notice that you don't pass the vertical line test. Clearly, this is not a function. It can't be. However, we can still talk about what's actually happening at the point 3, 2. And if you want, we can even add to this. If I go to number 2, we came up with the equation for our tangent line, 8/9 x minus 2/3. So y equals 8/9 x, so x minus 2/3. What you can see here, actually this is really cool, is at the point 3, 2, I'm hovering over it right now. Hopefully you can see my hover. If you hover over the point 3, 2, it'll kind of highlight that for you, and you can see how y equals 8/9 x minus 2/3 is tangent to the graph at this point. Now, of course, it runs through the graph. Also, it intersects the graph down here. It doesn't matter. All we care about is the equation to the of the tangent line at the point 3, 2. So that's what you're seeing here. I guess the reason I'm showing you this on Desmos is because you cannot actually graph this on your TI because it's not a function, and they're there are weird ways of going about it. If you have an end spire, your end spire will kind of do stuff like this. It's not as clean. I mean, with Desmos, it's very quick and it's very user friendly. If you want to get the squared, you just use the caret. So it's like Shift 6 and it'll square it and cube it and do whatever else for you. But anyway, just kind of a cool way that you can do a visual check of your work and kind of see exactly what this does. Sometimes I hate just going through math and being like, here it is. It's an implicit derivative. Just trust me. Sometimes it's nice just to be able to see it. Even though looking at the graph, still it's an abstract concept. But I want to make sure that you understand that there are tools available to you to help you visualize these things that maybe you can't do in your TI. I'm going to unshare this. Does anybody have a question about how I obtained this or any questions about this example? So we're going to do a trig one next, which I love. Just making sure. So this will be B. Oh, I've got a good one for you. It's never good when I say that, right? Sine squared 3y equals x plus y. And we're going to look at this at the point 2 minus pi over 4 pi over 4. I don't know why this one's so complicated. I can't remember. There was some reason why I chose this particular point. I think because it's hard to come up with good examples for these implicit derivatives because the equations are so weird. Maybe I just solved for it and it came out this way. This is one of my oldies. Now, anytime you see a trig function being squared, I highly recommend, and if you saw this in the office hour, you saw it there, you saw it on the notes for 3.1, that you rewrite it as a quantity being squared. Otherwise, you're not going to see the chain rule usage very clearly. So we haven't taken a derivative yet. I'm just rewriting the original equation so that we can take its derivative. I'm sure that's clear. Okay, now, again, if you're not quite sure exactly what's in store for you, just start taking a derivative and kind of see where it takes you. But if we're kind of mentally going through what's going to happen here, we're going to use the power rule. We're going to bring the 2 out front. We're going to have an inside function that remains the same, and we're going to decrease the power by 1. And we're going to have to take the derivative of the inside function. Note that the inside function also has an inside function. So this is very much like the example that I did in the office hour. I think it was number 8. I can't remember. Maybe 24, maybe it was 24. Something like that. So start by using the power rule. Bring the exponent out front. And then you have sine 3y to the first power. Now, I'm dropping the brackets for now just because I know that I'm decreasing the power by 1. So I just have sine 3y. Sorry, did I say x? I'm very used to saying x. It's sine 3y. And then if you want to pop the brackets back on, because maybe you have an easier time seeing it as an inside function, pop them back on. That's fine. The derivative of the inside function is 3 times the cosine of 3y. If that's too much for you right now, we're going to go ahead and just denote this as the derivative with respect to x of sine 3y. And then we'll find it in the next step. Because this is where our dy dx is also going to come in. Because when we take this derivative, we're going to have to chain on that dy dx. So don't think I forgot about it. We're going to pop it in here when we're done. Okay, so we use the general power rule, 2 times sine 3y to the first, and then we'll take the derivative of the inside function in the next step. The derivative on the right-hand side is 1 plus dy dx. Questions so far? Okay. So I'm going to write this now as 2 sine 3y. And to take the derivative of sine 3y, I would take cosine 3y and then chain on the 3. And I'm always worried that you're going to multiply this in, which is why I put brackets on here. The brackets are non-essential. I just don't want you to multiply the 3 into the 3y. Don't forget to chain on your dy dx because you just took d dx of a function written in terms of y. You must pop a dy dx onto that side. And note, by the way, that this is all just one long factor. Nothing ends up having to get distributed here at all. Because you don't have multiple terms. There are no pluses and no minuses, just multiplication. Which of course we're going to simplify before we start to solve for dy dx. Okay. If you have questions, your question would have already occurred here. Does anyone have a question here? Because after this, it's just algebra. Okay. So the cosine 3y times 3 was the derivative of sine 3y, and with the dy dx on it, of course. So I'm going to take the 3 and the 2, these two, and I'm going to multiply them together to give me the 6 in front. And I'll have 6 sine 3y cosine 3y dy dx. And you know, you can rewrite this as many times as you need to. I also need to have all the dy dx's on one side. So I'm just going to move this one over. It doesn't make sense to move them to the right and then move the only constant I have to the other side. So I'm going to write this as 6 sine 3y cos 3y dy dx minus dy dx equals 1. Change the sign, change the sign. Now factor out the dy dx and solve. And like I said, if you feel comfortable doing this, because I know you're like, oh my gosh, how many times can I possibly rewrite this same function? That's fine. Factor and solve in one step if you want to do it that way. Okay, whatever. Dy dx is 1 divided by 6 sine 3y cos 3y minus 1. Now we have some work to do here. First of all, I wanted you to find the derivative at the point 2 minus pi over 4, pi over 4. Now, lucky for you, this is the x coordinate, that's the y coordinate. We don't have any x's in this expression. That's why you're lucky in this case. We're going to evaluate this at y equals pi over 4. Now, usually I say we're going to evaluate it at this point because usually we have x's and y's in the expression together. In this case, we just have y's, so you just need to focus on y. So this is 1 divided by 6 times the sine of 3 pi over 4 cosine 3 pi over 4 minus 1. Now, the sine of 3 pi over 4, remember 3 pi over 4 is in quadrant 2. The reference angle is 45 degrees. The value of the sine is root 2 over 2. So it's positive root 2 over 2. But cosine in quadrant 2 is negative because the x values are negative. So we'd be looking at negative root 2 over 2 in that case, and then minus 1. This is where you have to know your trig values. Yes, Renee?
Shouldn't it be 6 sine pi over 4 and cosine pi over 4 minus 1 instead of
Well,
3
I
pi
had
over 4?
3y.
Oh,
It's
okay.
the 3y's. That's what does it.
Okay.
But thank you for checking, because I do crazy stuff all the time. My mind is all over the place. So I always want you guys to check in with me if you feel like I've done something weird. Anyone else questions here? We got to simplify still. Okay, so a negative times a positive is a negative. Root 2 times root 2 is 2. 2 times 2 is 4. 2/4 is 1/2. 1/2 times 6 is 3. And your slope, wait, negative. Interesting. Your slope should be negative 1/4. All right, now we're going to use that slope with your point to come up with an equation for the tangent line. You don't have to get too crazy with it because you've got a really weird point that you're dealing with. So I'm going to remind you of what your point is. So your slope is negative 1/4. Your point is 2 minus pi over 4 and pi over 4. Oh, by the way, students are always wondering, and I should just make a comment about it now in case anyone's stewing over it. Remember that if your denominator is negative, you can pop that negative into the numerator. So 1 over negative 4 is the same as negative 1 over 4, which is the same as negative 1/4. So remember that that negative can be placed anywhere in the fraction as long as it stays negative. It doesn't, as long as it doesn't get removed, then that's fine. All right, so here we go. We're going to take y minus y sub 1 equals m times x minus x sub 1. And we're going to simplify. Like I said, it's not going to look beautiful just because this is kind of a weird point, but that's okay. Do the best we can. Distribute first. Now, it's kind of up to you how you do this. I might just say take a negative times a negative as a positive, multiply the denominators together to get 16, and then the numerator can just stay 2 minus pi. I feel like students are always confused about what happens here when I distribute. So 4 times 4 in the denominator gives you the 16. And the negative times a negative gives you a positive. And then 1 times 2 minus pi is 2 minus pi. If you kind of break it up like that, it makes it a little bit easier to see. Don't feel like you need to split this up into 2 terms. You can, but you don't have to. Like I said, WebAssign accepts a lot of crazy stuff. I always want things in the slope-intercept form. For something like this, I would be a little bit less precise about that, just because it's a little bit harder to get into that form. So plus 2 minus pi over 16 plus pi over 4. And then you can combine these two by rewriting pi over 4 as 4 pi over 16. And then you can add these two fractions together by keeping the same denominator and adding their numerators. And that's about as far as I would want you to go with this. So we have negative 1/4 x, and then plus negative pi plus 4 pi is 3 pi. You'd have 3 pi plus 2 divided by 16. And that is just fine. Okay. I mean, I have one more example of an implicit derivative. I feel like it's really, you've kind of seen everything at this point. I don't really know if I want to go over it. I do have 10 minutes, but you know what? Actually, let's do it because it involves a rational exponent. I'm sorry, I've set you up for excitement and I've let you down. Very sorry. It does involve a rational exponent, so we should probably just do it. Just, you know, we'll just do it. All right, last one, you guys. Twice x plus y to the 1/3 power equals y. And we'll look at this at the 0.44. All right, so we're looking at this and we're noticing chain rule is going to be needed because we're going to bring that power down and we're going to have to multiply by the derivative of the inside function. But we don't need the product rule in this case because the inside function is a sum of two quantities and not a product. All right, so let's go ahead. Twice 1/3, leave the inside function alone, subtract 1 from the exponent. Now multiply by the derivative of the inside function. The derivative of x plus y is 1 plus dy dx. Equals, and the derivative of y on the right-hand side is dy dx. And I feel like we've come full circle here because notice that now you have dy dx and another term that are all getting multiplied by a quantity. That is when you know you're going to have to distribute. Now, it is up to you how you would like to write your function. If you are struggling with it in the denominator, you might want to make this a positive exponent. And I'm sorry, if you're struggling with it in the numerator, you might want to make it a positive exponent and push it down into the denominator. I mean, it might be helpful. I'm going to do that, I think. So I'm going to write this as 2 divided by 3 times x plus y to the positive 2/3. And that quantity is getting multiplied by 1 plus dy dx. And it might help you to kind of see more clearly now that you need to distribute. Questions here? All right, so let's go ahead and distribute. We're going to multiply this quantity by 1 and then by dy dx. So we'll have 2 divided by 3 times x plus y to the 2/3 plus 2 divided by 3 times x plus y to the 2/3 dy dx equals dy dx. So just lots of writing here and rewriting. If you want to get it right, you have to keep rewriting it. You don't want to miss anything. It's easy to lose stuff here or to make an algebraic misstep. Okay, I want all the dy dx's on one side. This guy is already over here, so I might as well leave him and then just move this dy dx from the left to the right. So I'm going to do that. So I'm going to leave that person over here, that little quantity. On the right-hand side, I'm going to have dy dx minus 2 divided by 3 times x plus y to the 2/3 dy dx. So not a whole ton is happening in each step, just little things here and there. Now, if you want to factor and solve here, that's fine. Oh my gosh. I'm going to factor the dy dx out of the right-hand side. And then we'll solve by dividing each side by this quantity, 1 minus 2 divided by 3 times x plus y to the 2/3. You're going to get a complex fraction, but we luckily know how to simplify those, so no big deal, right? Dy dx is 2 divided by 3 times x plus y to the 2/3. That's getting divided by 1 minus 2 divided by 3 times x plus y to the 2/3. Questions here? This is technically your unsimplified derivative. It's a complex fraction. On your test, I'm going to say find dy dx and then find the equation of the tangent line if I ask you to do so, because I can't, it's hard for me to award points if you technically find dy dx here and then you find the equation of the tangent line by plugging in 4 and 4 here, because technically you can do that and solve for dy dx, and then I'm like, great, well, I put in points for this, and then it gets very confusing. So I'm going to multiply through by my LCD so I can get rid of the complex fraction. My LCD is 3 times x plus y to the 2/3. I'm going to multiply every term by that quantity. And since I'm just multiplying by a value over itself, I'm not actually changing the expression at all. It's just getting multiplied by this quantity over itself. Okay. Now, once I've done that, I'll get those to cancel where needed, and then I'll simplify my derivative. We'll plug in the point. We'll find the equation of the tangent line. So all that's left in my numerator is 2. In the denominator, we have 3 times x plus y to the 2/3 minus 2. So that looks much better. Let's go ahead now and evaluate this at 4, 4. Does anybody have a question here? Morgan, go ahead.
Where did you get the minus 2 from?
From this piece in the denominator. So I have the 3 times x plus y to the 2/3 times 1, and then minus, and then these two canceled, and I still had that 2 in that numerator, so it just became 2 there.
Oh, okay.
Do you see it now?
Yeah, I was looking at it wrong.
Okay. I am glad you asked. Any other questions there? Okay, so to get the slope, I'm going to evaluate this quantity at 4, 4, which was the point that I gave you. So we'll have 2 divided by 3 times 4 plus 4 to the 2/3 minus 2. And then we'll simplify. 8 to the 2/3 is 4. You'll see that hopefully enough that you become familiar with it. It's the cube root of 8 squared. I'll rewrite it for you because I gave you that exponent rule earlier. So the cube root of 8 squared or the cube root of 8 squared, it's up to you. You can write it either way. But that's 8 to the 2/3 power. The index is the denominator. The numerator is the exponent. Two divided by 3 times 4 minus 2 is 2/10, which simplifies to 1/5. That's your slope. And then you'll just write the equation for your tangent line the way that you always would. One-fifth x minus 4/5 plus 4, which is 1/5 x minus 4/5 plus 4 is 20/5, so plus 16/5. And again, if you wanted to, you could pop this equation into Desmos. Twice the quantity of x plus y to the 1/3 equals y. And also pop in your equation for the tangent line and graph it and verify that it is indeed the tangent line at 4, 4. But I don't have time for that. You guys have a quiz on Thursday. I mean, that's tomorrow. Over 3-1, 3-2. Tomorrow, I'm going to do 3-3, which is a little shorter, and start 3-4. You're going to finish 3-4 in your asynchronous work over the weekend. And I don't see you Monday the 5th, but you'll be back on Wednesday the 7th for your test over the 4 sections that we're covering out of chapter 3. It's got 5 sections, but we're skipping 3, 5. It's short. It's inconsequential. So I'm not worried about it. It used to be optional. I don't know why maybe it is still optional and I just covered it because last semester. All right, that's all. I'll see you tomorrow. I'll put up some homework for you from 3-2. Have a wonderful evening.
When's the homework for the weekend due?
The homework that I'm assigning today or the homework that I'm assigning? Oh, that's a good question. You mean because I don't see you Monday?
Right.
Yeah, then we'll just have it due Wednesday. Yeah, I'm glad you asked.
Okay.
Yeah, so whatever I assign tomorrow and over the weekend, we'll just have it be due Wednesday. It doesn't really make sense to have it due Monday if we don't have class, and then your test is Wednesday, and then you can't practice it anymore.